let's take another 5 minutes and then we will start. Have you followed your team yet?
Yeah.
Okay, great.
Yeah, we did it last time.
Okay, that's great. How many members?
Main page, because we work together as well, so it's a lot easier.
Yeah. Okay.
Yeah, I think they got the first one due Sunday.
There's Sunday midnight.
Yeah, whatever. I made a start on it, but I don't know if my.
You haven't started yet?
No, I made a start, but I don't know if my formulas are correct on the Excel.
Oh, okay.
Give me a second, I'll figure it out.
Okay, now let's start our lecture. Last week, we discussed about 2D elements, right? And all of you guys agree that triangle 2D element would be the simplest and the most accurate element. But is that true? Of course, triangle 2D element is definitely the simplest 2D element. But is this one the most common used and the most accurate element for 2D problems? Okay, actually, the answer is no. The most common used 2D elements is actually the quadrilateral shape or the rectangular elements. Why rectangular elements is more common used than triangle one? Okay, think about it. For example, we have a 2D problem. And like what we practiced last week, just a very thin plate, a rectangle plate. Remember last week when we solved this problem, we break down this structure into two triangle elements, right? The first one and the second one. And recall how we derive those matrices. For the numerical method, one of the most important equation is the shape equations. And for the triangle element, we have to make sure we use the correct shape functions to solve the problem. And for the triangle element, we assume the displacement is linear distributed. In that case, we have this equation. The displacement in x direction equal to ax plus by plus c. Okay, x and y are the coordinates of a certain point. U is the displacement of that point. A, B, C are constants, right? And to solve this problem, we need to find out the displacement at 3 nodes. Then we have 3 equations. U1 equal to ax1 plus by1 plus c. And then U2, U3. Based on those 3 equations, we can solve for A, B, C, those 3 unknowns, right? Okay, and now may I ask, those 3 constants, A, B, and C, in element 1 and A, B, C for element 2, are they the same or not?
Some of them.
They cannot be exactly the same,
No,
right?
No, all 3 of them.
Maybe some of them are the same, but definitely not all of them. Now, assume that we have a big 2D problem, and you may need to use thousands, even millions of triangle elements to solve the problem. Then, think about how many calculations you need that. For each of the elements, you have to calculate the ABC for the element, and you have millions of elements. Then you have to do the same calculation millions of times. Think about it, how big the work it is. Okay, now let's have a look. What's the benefit of using 2D element? Now, rectangular element. What's the benefit of using rectangular element? Okay, actually, rectangular element is a special quadrilateral element. But let's have a look at this element first. We have a 2D element shown here. Okay, this is our rectangular element. The same, there are 4 nodes, and we have to number those 4 nodes counterclockwise. So if this is node 1, then the second one must be the one. The second node must be this one. And then third one, fourth one. So we have to number that clockwise. Okay, and now if we have a rectangular element, we use the same assumption. We assume the displacement is linear distributed. In that case, we have this equation. This is actually just a mathematical method. So if we assume the displacement is linear distributed, the displacement u, which is the x directions deformation, equal to a plus bx plus cy plus bxy. Okay, look, we have 4 constants, a, b, c, d. And also for this element, we actually know the displacement of those 4 nodes. So we have 4 equations and 4 unknowns. We can solve for those unknown constants, a, b, c, and d. Okay, then we need to rearrange this equation. Instead of using equation sets, we can use matrix format to represent it. Okay, then we have 4 equations and 4 unknown. We can solve for a, b, c, d. Okay. Here, let's think about it. When we have a rectangular element, this rectangular element can be located at any place, right? But assume that we have a very, very special element, and this triangle element is located at the center of the coordinate system. Say the center point of this rectangular is the original point. In that case, actually we can find out what the height and the weights of the element are, right? Let's call the height h and the weight b. Okay. In that case, we can do something and we can find that if the coordinate system is located at the center of this rectangle, and we know the weights, 2b and 2h. The weight of this rectangle is 2b. The height of this rectangle is 2h. Then we can find that the first coordinate, the coordinates of node 1 is definitely minus b minus h, right? Similarly, the second node has the coordinates of b minus h. Then the third one is b and h. The fourth one is minus b and h. Okay. Then we substitute those b and h to this matrix equation. We can find that the shape functions or the interpolation functions for 2D element are those n's. N1 equal to b minus x times h minus y over 4bh. And N2 have a similar equation, b plus x times bh minus y over bh for bh. And N3 and 4. Okay, now, if we rearrange this equation, then we can find that the displacement u can be calculated by using N1 times U1 plus N2 times U2 plus N3 U3 plus N4 U4. Recall what we have discussed last week. For the triangle element, how we calculate the displacement then? For triangle element and the rectangle element. For triangle element, we have the equation u equal to n1 x u1 plus n2 u2 plus n3 u3. V equal to n1 v1 plus n2 v2 plus n3 v3. Now, we move on to the rectangular element. We get the same or very similar equations. To calculate the displacement in x direction, we need to use n1 u1 plus n2 u2 n3 u3 plus n4 v4. Okay, u4. To calculate the vertical displacement, we need to use similar one, n1 v1 plus n2 v2, like this. Okay, now we can find that for the triangle element, we have 3 nodes. So we have 3 shape functions, n1, n2, n3. And for the rectangular element, we have 4 nodes, and there are 4 shape functions. Okay, so this is a very important behavior for the shape functions. The number of shape functions equal to the number of nodes in this element. So for the 3 nodes element, you have 3 shape functions. For 4 nodes element, you have 4 shape functions. Later, if we have 10 nodes in one element, that means you have 10 shape functions in this element. Okay, now we have the shape functions, but as I mentioned, these shape functions, those 4 n's are for a very, very special rectangular element. If we want to use those n1, n2, n3, n4, we have to make sure this is a rectangular element, and we have to make sure the coordinate system is located at the center of this rectangle. So the problem comes, how can we have so many such special rectangular elements when we solve the problem? Now, assume that I only have a general rectangular element. And we know this rectangular element, those are the 4 nodes. Node 1 has the coordinates of x1, y1, x2, y2, x3, y3, x4, y4. Okay, this time, the coordinate system is no longer Oh, okay. This time, the coordinate system is no longer located at the center of this rectangle. For example, the origin point of the coordinate system is located here, somewhere, not the center. Then, how do we update our coordinate system? How do we update the shape functions for this rectangular element? Okay. For this special element, the red one, we know the shape function can be calculated by using the element's weight and the height, right? For this element, the weight is 2b, the height is 2h. And the coordinate system is at the center of this rectangle. If we have this element, and we can easily find that the shape functions for this element are this, okay, N1, N2, N3, N4. But now we have another one. This one is still a rectangular element, but not that special. The coordinate system is no longer located at the center of this rectangle. Then what we can do? Of course, you can use the very basic equation. We use this equation u equal to ax plus a plus bx plus ay plus bxy. Of course, you can reuse this equation and recalculate ABCD and rederive shape functions. But actually, we can do another way. Now, the globe coordinate system is x and y, right? Why not we create another coordinate system and we let the other coordinate system located at the center of this element? For example, I create another one. I call this coordinate system, instead of x, y, I call it s and t. Right? I can create another coordinate system. And I like this coordinate system as t, coordinate system located at the center of this rectangle. Can I? Right? Definitely I can. And now, this element is moved to like this, right? Now, may I ask for this black element here, what is the width and what is the height of this element? What is the width of this element? Sorry. It's x2 minus x1. And the height of the element is y3 minus y2, right? Of course, you can use y4 minus y1, but you should have the same number. Okay, now, in that case, if we let 2b equal to x2 minus x1, 2h equal to y3 minus y2, then b equal to half of this and h equal to half of that. Then we can substitute bh to this equation, right? So we have n1 equal to 4bh. B is this one, copy. And then on the top, we need to use b minus and h minus y, right? Okay, now if we create a new coordinate system x and t for this element, and then actually we move this rectangular element to the center of the new coordinate system. And then we can use this kind of shape functions to do the calculation. But for this one, n1 equal to b minus x, h minus y, right? And in this new coordinate system, this is a b, this is the h. And we need to use b minus what? Is that x?
Yes.
X, right? Because we used a new coordinate system. So the shape function is now changed to this one. And the variables are no longer x and y. They are s and t, right? Okay. Now, I let you know that this coordinate system ST is named the local coordinate system of this element. But actually, we can do one more step. We scale the coordinates. So this time we make the element the new system more complicated. Okay, so this is the global coordinate system x and y, and this is the new coordinate system s and t. And this time we use two ratios to scale xy to st. And the ratios are here. X bar is the distance from the central or the origin point of the global coordinate system to the local coordinate system in X direction. And we have another one, Y bar. And then we make this length. For example, as we discussed, the length of this rectangle equal to Y x2 minus x1, and the height equal to y3 minus y1, y2. Right? And now we make this number equal to 1, 2. So in that case, this rectangular element in its new coordinate system is no longer a rectangle shape. It is a square shape. And the length and the height of this square will be 2. In that case, we can confirm that in its local coordinate system, the first node always have the coordinates of -1, -1. And the second node has the coordinates of 1, -1, then 1, 1, -1, and 1. By using this way, we can find that the shape functions in the new local coordinate system are those. N1 equal to 1/4 times 1 minus s times 1 minus t. N2 equal to that one, and then 3 and 4. Okay, now let's have a look at those equations. This is the shape functions in its local coordinate system, and sometimes we call it neutral coordinate system. So they are the same thing. In different textbook or articles, they call it differently. But neutral coordinate system and local coordinate system, they mean the same thing. Okay, now in its local coordinate system, those are the shape functions. And like what we have derived, this is the shape function for a normal rectangular element and in the system. Which one you want to use? This one, or this one? Secondly, the shape functions in its local coordinate systems are the simplest, right? And this is also the reason why we want to use rectangular elements other than triangle elements. For the rectangular element, if we solve the problem using its local coordinate system, we can simplify the calculations a lot. But for triangle element, it's very hard to derive the equation for its local coordinate system. So this is the benefit of using rectangular element and also the benefit of using local coordinate system. Sometimes we have to deal with a lot of shape function matrix, shape functions calculation. Actually, we need to understand some basic behaviors of the shape functions. Look, we have those shape functions N2, N1, 2, and 4. Okay, first of all, for any kind of element, the number of shape functions equal to the number of nodes in the element. Say for triangle, we have 3 nodes, then we only have 3 shape functions. For rectangular, we have 4 nodes, of course, we have 4 shape functions. Later, we will discuss the higher order one. If we have 10 nodes in the element, then we have 10 shape functions. And another property is when we finish calculate the shape function for a certain point, you can find that the sum of those shape functions is 1. For example, I give you a random point, say, for example, 0.5 and 0.5. Okay, you substitute 0.5 and 0.5 to those equations. You have N1, N2, N3, and 4 values, right? You sum them together, 100%, it must be 1. If not, okay, you make some mistake. You have to check if you make some calculation incorrectly. And another thing is why we call them shape functions or interpolation functions. And also why we call them N1, N2, N3, N4. Okay, this is because if you substitute the coordinates of the node to those equations, for example, we substitute the coordinates of node 1 to N1. You will find that N1 equal to 1 and all the others equal to 0. The same, if you substitute the coordinates of node 4 to those equations, N4 is 1 and N1, N2, N3, they are 0. So those are some methods how you check if your shape function is correct or not. Okay, now we know in the rectangular element, we have the shape functions. And if we want to use those shape functions to calculate the displacement, okay, we need to use those equations, right? So to calculate the displacement in x direction, we need to use N1, U1 plus N2, U2 plus N3, U3 plus N4, U4. And if we write it in the matrix format, here it is. So the displacement equal to the shape function matrix multiply the node displacement matrix. Okay, and now if we have the displacement already and we want to calculate the strain and the stress, what should we do then? Exactly the same as triangle element. We need to use the strain displacement relationship to do the calculation. In that case, we need to use B matrix. B matrix multiply the node displacement matrix, we can get strain. And to calculate stress, easy. We just need to use the stress, the material matrix multiply strain. Then we have the stress. So for triangle element, To calculate displacement delta, we need to use the shape function matrix multiply the node displacement matrix. Similarly, for full node element, to calculate displacement, we need to use shape function matrix multiply node displacement matrix. But the difference is the size of those matrices are different. For triangle element, the shape function matrix is a 2 by 6 matrix. But for full node rectangular element, the size is 2 by 8 element. And to calculate string, we need to use B matrix multiply the node displacement matrix. The same string equal to B. And for triangle element, B matrix is a 3 by 6 element. And for full node element, B matrix is a 3 by 8 matrix. To calculate stress, we need to use B matrix multiply string. And for rectangular element, we use the same equation, right? And don't forget this D matrix related to the type of those 2D problem. If this is a 2D plane stress problem, you have to select the D matrix for plane stress. If this is for plane strain, you have to use the D matrix for plane strain. But other than that, no matter it's triangle element or rectangular element, this equation remains the same. Okay, now, actually, I think you may already notice something. Look. I want you to have a clear look at those two sides of equations. To calculate the displacement at a point x and y, we need to use n1 xy times u1, right? N2 xy u2 and 3 and 4. Let's look at these shape functions. It is equal to n s and t, right? So the displacement equation is based on the globe coordinate system x and y. The variable in the displacement equation is the variables are x and y. But in our shape function equation, they are s and t, right? So we have to be very careful which variables to be used for the certain calculation and how we convert st to xy or the other way. Okay, how? We will discuss later. And now let's think about another case. See here, we have a shape like this, a quarter circle. And I want you to create a model to solve this problem. Of course, we can use triangle element, right? And the triangle element can match the curve. Very good. But how about rectangular element? How about rectangular element? If we are keen to use rectangular element, very likely we will receive the mesh like this one, right? Because we keen to use rectangular element. And if we use rectangular element, the shadowed area cannot be created, right? We cannot really create a curve or a very closed shape as the real shape. We may have to use some shapes like this, or this, or this to match the shape. But they are not the rectangular element, right? They are still quadrilateral four-node elements, but not rectangular elements. Then, if we have to use those elements, what are the shape functions? And for those kind of elements, do they have its local coordinate system? And how it looks like in its local coordinate system? Okay. Let's have a look. Assume we have a general quadrilateral element, okay, like this shape, the left one. In globe coordinate system, we use the variable x and y, right? And the displacement is also in x direction and y direction. And the shape of this element, let me highlight the shape. Okay, this is the shape of this quadrilateral element. For this element, if we do the calculation in the globe coordinate system, okay, we have to know the coordinates of each node, and we have to calculate the constants and then derive the shape functions. It's painful, really, really painful. We have to spend a lot of time to do the calculation. But if we can map this rectangular element to a certain coordinate system, and in this coordinate system, this quadrilateral element have square shape, and the length width that both 2. In that case, the calculation would be much easier, right? Now, the problem is how we convert this quadrilateral element from the XY globe coordinate system to the ST coordinate system. Okay, here we have an association. We will use the linear mapping method for that. Okay, now assume we have a point P. This point P is inside this element, the blue element. And we do know that this point P have the coordinates of X and Y in globe coordinate system. And now we want to know where is P in its local coordinate system. Here, we use linear mapping association. If we use linear mapping association, what we have is in the globe coordinate system, we know the point P has the coordinates x and y, right? Okay. The linear association gives us this. X can be calculated by using S and T. The equation is A plus BX plus CY plus DXY. Oh, sorry. BS CT DST. ST are the variables in its local coordinate system. A, B, C, D are four constants in this equation. Okay. Now, how do we know what A, B, C, D are? This will be exactly the same as how we derive the shape functions, right? We know the node 1, the first node has a coordinate of x1, y1, right? And we 100% sure in its local coordinate system, node 1 has a coordinate of -1, -1. So, to calculate A, B, C, D, we definitely know that x1 equal to A is the constant, right? Plus B constant times S. The coordinates in ST coordinate system, so -1 plus C times T, which is -1 plus D, -1 times -1. Right? So this is the first equation. Similarly, we can write down the equation for x2, x3, and x4. Then we have 4 unknowns and we have 4 equations. We can solve for A, B, C, D. Okay. If you do try that, you will find this. To calculate x, to calculate x, we need to use something times x1 plus something times x2 plus something x3 plus something x4. Okay, and then look, the expression of this equation is very, very similar to the equation we use to calculate displacement, right? So here, to convert the coordinates from S and T to X and Y, we need to use those equations. The coordinates in XY coordinate system equal to the shape function matrix multiply the node coordinates. Okay, you have to be very, very careful. Those n's are the function in terms of the variables s and t. And this is how we convert st to xy. Okay. Then when we do the calculation of displacement, it depends. For example, if we want to calculate the displacement at a certain point, at point P, we need to use the shape function matrix multiply the node displacement matrix. Okay, this equation is not very clear, so let me rewrite it. To calculate the displacement matrix at a point, for example, at point P, we need to use the shape function times node displacement matrix. But the shape function is actually a function in terms of variables s and t, right? So the displacement u and v, they are the displacement in x direction and y direction. So how do we calculate the displacement in globe coordinate system using the coordinates in its local coordinate system? It's kind of complex, right? So you have to be very careful. If you use this equation to do the calculation, you have to be very careful with what's the variables in the N matrix. If point P the given point P is in globe coordinate system. For example, you know the point P is located at xp, yp. You have to make sure those shape functions are using the variables x and y. If this P is given in its local coordinate system, then you have to make sure those n's are the shape functions in its local coordinate system. Okay, now let's have a practice. Let's have practice how we convert st to x and y. Okay, now let's have a look at this question. We have a quadrilateral element in the globe coordinate system. Okay, and all the coordinates are given. Now, I want you to find a point P. And what we know is this point P in its local coordinate system is located at 1 and 0.5. Where is P in this real element then? Okay. So this is the quadrilateral element in the global coordinate system. And this is the element in its local coordinate system. And in its local coordinate system, we know there is a P located here. And the coordinate is 1 and 0.5. I wonder where is P? Here. Make a guess. Where is P?
Right edge.
On the right edge, right? Why? Because P is on the right edge, right? Okay, yes. P is on the right edge. Where is that? Yes, P is on the right edge, right? Great, we all agree with that. Okay, then which point is that? For example, is P located at the center of the edge? No, right? Or yes, right? Because look, P is located at the quarter place of the right edge, right? So similarly, it would be here. Okay, of course. For this P, we can use this way to find the coordinates of P in its local coordinate system. And now if I'm asking, where is Q? And this Q has a coordinate of 0.5 and 0.5. It's very hard to guess this time, right? So if we have point P here, okay, somehow we can guess it's here, and then we do some calculation, we know where P is. But I have another point, the red point Q. We know it is inside this element, but where exactly it is? It's very hard to guess, right? Okay, now we need to use shape functions. Now, to guess where P is, this is what we did, right? So we know P is located on the edge 2, 2, 3, no 2, 2, 3. And then we know P is located at the corner, a quarter distance to a point. So we can do the calculation. But actually, we do have another easier way to do the calculation. We can use shape functions. Okay, now now I want you to try to use shape functions to calculate where P is. Okay, all the equations are given. We have 4 shape functions, n1, n2, n3, n4. And to calculate x, we need to use the shape functions multiply the x coordinates of those 4 nodes. To calculate y, we need to use the shape functions multiply the y coordinates for each node. Okay, I give you 2 minutes. Can you please try yourself first? Okay, here's my answer. The same? So x equal to 2.625 and y equal to 1.75. So this is the coordinate of P. And at this point, N1 equal to 0, N2 equal to 1/4, and N3 equal to 3/4, and then 0. Actually, here, every time when you finish calculating the shape functions, I want you to double check the results. Say all those numbers are either 0 or positive number. If your calculation, for example, you finish the calculation, you find N1 equal to -2. Okay, 100% it's wrong. And the second thing is all those four numbers are between 0 to 1. So if you have a number greater than 1, say for example, N2 equal to 2 or 1.1, it's wrong. Okay? Then you can add those four numbers together, sum N1 to N4, and check what's the value. 0 plus 1/4 plus 3/4 plus 0, 1, right? So this is how we check if our shape functions are correct or not. Okay, now we find a method how we convert the coordinate from ST to XY, right? Okay, now I have another question. I have a point P, not P, another point Q. And this point has a coordinate of 2 and 1.1. In XY coordinate system, I wonder what is this point in ST coordinate system?
Yes, you do the same thing. Well,
Mm-hmm.
solve for the shape function. Really complicated.
It looks very complicated this time, right? We have a certain equation to calculate SXY from S and T, and we don't have this, the reverse equation, right? Okay, but how do we solve this problem? Easy. Let's have a look. Actually, you already complete the numerical method, right? So I believe you still remember a matrix called Jacobian matrix. The Jacobian matrix is actually the equation used to transfer ST to XY or vice versa. So by using Jacobian matrix, we can easily convert the coordinates from S and T or XY to S. Okay, now let's have a look how Jacobian matrix works. When we do the calculation, we actually do all the calculation in the coordinate system X and Y, right? Say for example, if we want to calculate the displacement or the node force or the node displacement, we can easily get the solution from its local coordinate system directly. So we don't have to convert ST to XY or XY to ST. But we have to calculate stress or strain, right? Stress and the strain, we have to get the solution in the global coordinate system. So the stress in XY direction and suggest in ST direction. They are totally different. So after we finish the node displacement calculation, we need to convert the displacement, all those solutions from its local coordinate system to the globe. Then we have to use the Jack-Bin matrix. Okay, actually, Jack-Bin matrix is derived this way. When we do the calculation of string, we know the displacement U when we calculate the normal string in x direction, the relationship between string and displacement tells us that to calculate the normal string in x direction, we need to use partial u over partial x, right? But when we do the calculation, u is calculated based on s and t, right? So u is actually a function of s and t. This is not a function of u with x and y. So what we can do? Okay, and according to the practice, the example we just practiced, we know that x is actually a function of s and t, right? And y is also a function of s and t. But if we do some transformation, we can find that s can be considered as a function of x, y, and the t the same. Right? Okay, now back to the string matrix. We know string epsilon x need to be calculated by using the displacement u over partial u over partial x. Now, this one is actually s. U is a function of s and t. But actually, how we calculate the displacement? We use shape functions, right? We use shape function n1 u1 plus n2 u2 plus n3 u3 plus n4 u4 to do the calculation. And the shape function n's, they are the function in terms of s and t. Okay, actually, s, the local coordinate s, can be considered as a function of x and y, right? So we can update this equation to this. Partial u is a function of s, and s is a function of x and y, right? Similarly, t the same. dx, partial x. Okay, recall what you have learned in mathematics. S and T are functions in terms of X and Y. When we do the differentiation calculation, we have this relationship, right? So partial N is a function of S and T over partial X. This one equal to partial N over partial S, and S is a function of X and Y. So partial S over partial X. At the same time, function N has another variable T. So partial N over partial T times T is a function in terms of X and Y, right? So we have this. Okay, similarly, to calculate partial N over partial Y, we can use the same method. So we have another equation, partial N over partial S times partial S over partial Y, plus partial N over partial T times partial T over partial Y. Okay, then we have two equations. Then, as what we did for the other part, we convert those equations to matrix format. So in that case, we have this equation. Partial N over partial S and partial N over partial T times this matrix equal to partial N over partial X and partial N over partial Y. The left side, the coordinates are S and T. The right side, the coordinates, the variables are X and Y, right? By using this method, we can convert the coordinates from X and Y to S and T. And this Jacobian matrix, if we calculate the inverse of this matrix, right? So if we have the inverse matrix of this, actually we have partial N I over partial X and the Ni over partial Y equal to the inverse of Jacobian matrix multiply partial N over partial S, partial N over partial T. So if we want to convert the coordinates from X, Y to ST, we use Jacobian matrix. If we want to convert ST to XY, we need to use the inverse of Jacobian matrix. Okay. Now, back to the string matrix. The string matrix are calculated by using the differentiation in terms of variable X and Y, right? If we want to calculate this string, we have to make sure the coordinates or the variables are X and Y. So if those shape functions are still in S and T, you have to use Jacobian matrix to convert them to X and Y. Then you can continue the calculation for stress. Okay, now we have another question. Remember when we solve 1D problem, we may have more than one element in the system, right? And we have to assemble the element stiffness matrix to the globe stiffness matrix. Similarly, for 2D problem, we have the same step. We have many elements in the system. We have to assemble the stiffness matrix K, right? But think about it. If we want to assemble something together, all those things must be in the same coordinate system, right? Which means when we solve the problem, we have to make sure this K is obtained in the globe coordinate system, right? Because individual elements, different elements have different local coordinate system. So to calculate K, you have to use the globe coordinate system. So you have to make sure B, 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 and A are obtained from X and Y. But actually, we have discussed a lot. The benefit of using 2D element because it's local coordinate system. The calculation in its local coordinate system is very simple, right? So we have to use Jacobian matrix in the calculation. When we assemble different elements together to solve the problem, the general equation is this one. The stiffness K equal to H times the integration through the whole area, B transpose times D times B, dA. But as I mentioned many times, those shape functions are given in S and T coordinate system. ST coordinate system are the favorite one. So instead of using dx dy, we need to use Jacobian matrix to convert this dx dy to ds and dt. And then update this equation here. So in that case, we convert x and y to s and t. So we can calculate this K matrix in its local coordinate system. And it wouldn't affect us, it wouldn't affect the assembling method when we assemble all the K matrix together. Okay, so this is how we calculate K matrix. And another thing is about force. For 2D problem, we can apply a point load, we can apply a pressure, we can apply a distributed load, right? But if we decide to use numerical method, we have to make sure the force matrix, the atoms in the force matrix are the point loads, right? But for the real case, there are body forces and the surface forces. So we have to convert those kind of forces to its equivalent loads. How? Okay, we have to use shape functions again. For body forces is the forces like gravity force or the magnetic force like this. And to calculate its equivalent node force, we need to use this equation. H, the thickness of the element, and then the determinant of the jet-in matrix times shape function matrix transpose times x. X is the force vector in the different directions, x direction and y direction. Okay, this is how we calculate the body forces. And for pressure or for distributed loads, we need to use this equation to do the calculation. So for surface load, we need to calculate the force integral in the load direction. And we use the shape functions of the nodes where the force applied times T, the pressure. Multiply LH over 2. L is the length, the real length of the element. H is the real thickness of the element. Okay, divided by 2. Okay. Now, let's have a look another example. We need to practice how to calculate the equivalent node force. Okay, have a look at this question. We have a quadrilateral element and we have a surface tension along the H223. The magnitude is 2000 psi. Okay, and now I want you to write down the node force matrix for this element. Maybe you can make a guess. What are the node force on each node? What are the node forces? Okay, just let's have a look at this case. So we want to find the equivalent node forces. May I ask, what's the size of this node force matrix? What's the size of it? 2 by 2 by 8. 2 by 4. Okay. First of all, for force, node force matrix is definitely a column matrix. So we can only have one column. But how many rows? Each node has 2 forces, right? So in total, 8. Okay. Okay, now can you tell me what's the force at node 1? 0, right? We can't find any force. 0 and 0, right? Because both x direction and y direction, they are 0. Okay, how about node 2? 2000 divided by 2. I think this is PSI, right? Means a pressure,
Yeah.
right? So, yes, 2000 divided by 2, it's still a pressure, right? This is a node force vector. It must be a force. So how we convert this force to, how we convert this pressure to force times length and the weights, right?
Yeah.
So pressure multiply area is the force. Okay, so if we want to calculate the force, you need to know what is the thickness of the element. It is given 0.1, right? And we need to calculate the length. Okay, so the length.
You have to get it using.
Yeah, so it's that easy to calculate?
Yeah,
5
squared.
4
4
3
squared plus
5, right? So I
30.
think 5 inch. Okay, so times 0.1, the thickness times 5, right? Because look, the height is 5. And this side is 3, right? So 3, 4. So this, the length 5. Okay. Okay, so this is the pressure, the node force at node 2, right? How about y direction? 0, right? How about node 3? Same, okay, same. And then 0, right? And how about node 4? 0, 0. Okay, so this is how we solve this problem. But this problem is not that hard, right? Because the force is uniformly distributed and the force is along x direction only. But if I want to make a challenge, we have another force. The other force has, okay, this time is a triangle pressure. Then how you convert this kind of force to the node forces?
I think you used the 2/3 rule or something. The uniform.
Yes, you're correct. That, yeah.
2/3 and then.
Yes, so you can use 2/3 here and 1/3. Okay, I make it more complicated. Then this time it's a curve, right? So it's not that easy to make a guess what it is. So we have to use the shape functions to help us to do that. Okay, now if we decide to use shape functions to do the calculation, we have to figure out which shape functions we need to use. We have 4 shape functions for this quadrilateral element, right? Do we need to use all of them? Actually, the force, the pressure is applied on edge made of 2 to 3, right? The force is not applied on the other edge. So we don't have to use all of that. We only need to use shape function 2 and shape function 3. Okay? Then we need to do a integration calculation. we do the integration calculation, they actually, to calculate the surface force, we need to do a double integration. But the pressure, because the thickness is constant, right? So we only need to, we can convert this double integration to a single integration. And the gap, we need to multiply the thickness h. Okay? And then, which variable do we need to use? In its local coordinate system, we have two variables, s and t, right? So, if we want to calculate the force in s direction, the force in s direction, we need to do the integration through t direction. Okay? Similarly, if we want to calculate the force in t direction, we need to use the okay, so you have to be very careful if you want to calculate the force along s direction, because when we solve the problem, we use s and t, not x and y. To calculate the force in s direction, you need to do the integration through t direction. If you want to calculate the force along t direction, you need to do the integration through x. Okay? Then let's have a look how we use shape function to solve this problem. Okay, in s direction, we need to use N2 and N3. But if you write down the shape function matrix, make sure this is the correct one. We use N2 and N3 only. But the shape function matrix include more items. N2, then 0. N3, then 0. The second row is the other way. N0, N2, 0, N3. Okay? Then after we finish the calculation, we can find the force in s direction and t direction. Okay. Okay, so this is how we convert the pressure to the equivalent force. And today, actually, we practiced two examples. Both not the first one. For the second question, we have to do many integration calculation, right? Do you like integration calculation when you learn your math subject? It's not that easy, right? And for some cases, for example, if I want you calculate okay, for example, I want you do a calculation. Y equal to the integration through -1 to +1 x squared dx. Okay, can you tell me what's your answer in 30 seconds?
X cubed is 3, right? Oh, no, it's still 0. X cubed is be X cubed, it'll be.
Okay.
It'll be.
Okay, tell me how you do the calculation. Tell me how to
X
do the
cubed over 3, isn't it?
1 by 3 x cubed, right? And then we have to substitute 1 and minus 1, right? So 1 by 3 times 1, then minus, right? 1 by 3 over 3. So 2/3, right? Okay, how long it takes? 2 minutes. Okay, not too bad, right? Now I want you tell me another one. Y equal to the integration 2x squared minus 2 divided by x plus 3. Okay, I give you 1 minute.
Then 2x squared, 2x cubed.
Okay, so dx. Do you think you can solve this problem in 2 minutes?
Yes.
You did? Okay.
Easy. But is that 2x squared or 2x cubed?
Square.
It's not just
1.5 minutes already. Okay, means time's up. So what's your answer? Okay, actually, not just us. The software or the computers didn't like such calculation at all. So no one liked it. So do we have some other method can help us or the computer to solve this problem quicker? Okay, actually, say for example, we have a curve or a function like this. The integration is actually the area of, for example, like the first one, x squared. I think the curve is like this, right? This is x squared. The integration is actually the area made of x-axis and the curve itself and the boundary, right? So the boundary is 1 and minus 1, and the curve is x squared, and then this integration is actually the area, the shadowed area, right? Similarly for the second one, the same, right? But if we want to calculate the area, okay, now assume we have another one. We have a rectangle. And this is minus 1, this is 1, and this is t, for example. Can you tell me what's the area it is? T times 2, right? So easy. 2t is the area. It takes our second to get the answer. But can we use similar method when we calculate the area like this? We can create several rectangles. For example, I create a rectangle, this one, and another rectangle, and then. And then we can get a Similar answer, right? May not be exactly the correct one, but very close if we have enough rectangles. Okay, now I just want to introduce the Gaussian method. The Gaussian method is actually using the same concept to do the integration calculation. For example, we have a curve, this curve, yx, okay? And then we want to calculate the area of the integration. We want to calculate the integration through -1 to 1, right? This integration is actually the area of this one. It's not easy to calculate the exact area of this shadowed area, but if we can create the rectangles, it's not that hard. For example, instead of calculating the exact shape area, we calculate the area of this rectangle. So we select a point from this curve. For example, when x equal to 0. We select this point. And we assume this is the height of this rectangle. And the boundary is from -1 to 1. So the width is 2, right? So height times width, we have height times width, we have the area. And we can use that as a approximate area of this integration, right? Okay, so definitely you can find the difference. The result may not that accurate, but it takes few seconds to go to the answer. So if we have enough rectangles, we could get the answer very close to its exact solution, right? But how many rectangles do we need? And which point should we select? Okay, Mr. Gauss already helped us to figure it out. According to the function, the real function, we need to decide how many points to be used. For example, for a very simple case, like y equal to x or y equal to ax plus b. For this linear curve, we can just use a single Gauss point, and we select the point at the middle point, 0. For if so, the weight of this point is 2, because the integration is from -1 to +1, right? The weight. But if we have another equation like we practiced, when y equal to x squared, if we use just one Gaussian point, when x equal to 0, y equal to 0. 0 times 2, 0. We can't use it. In that case, we need to select 2 Gaussian points. And those 2 points, you cannot use random point. You have to use the point x equal to 0.577, negative and positive. And the weight of, or the width of that rectangle is 1. Okay, so for this curve, x squared, and this is minus 1, this is 1. We need to select the point. Negative 0, 7, 7, and positive 0, 5, 7, 7. Okay, and then we use this as the height of the rectangle. And then the area of those two rectangles will be the integration of x squared from -1 to +1. Okay, actually this method is very, very useful when we do some integration calculation for a real very hard equations like those two. Okay, so if we use the mathematical method to do the integration, it takes out days or years, right? But by using Gaussian method, we just need to select certain points. For example, by using 3 points, we can get the solution. We don't have time to practice, but I like you to have a look at the solution. By using Gaussian method, we can use the value. We substitute the Gaussian points to the equation and get the number. Multiply the weight for that rectangular. And we have 3 Gaussian points, so we do that 3 times. Okay, and the sum of those 3 is the final solution. And we can compare the solution obtained by using Gaussian method and the real solution. Here's the difference. How small it is, right? So by using this method, we can get the integration very fast. And also this is the method used by the software. Okay. That's all for the lecture today. And today we discussed about the other 2D element, rectangular element. To be honest, 2D rectangular element is more common use than triangle element. And it is a better element which can give us the more accurate solution, which means you can use less number of elements to solve the problem and get a better results. Okay, next week, let's move on to the 3D element. Let's have a look. How many different types of 3D elements we can use and what's the difference? Okay, now let's have 5 minutes break and please come back at 2:10. We will start our tutorial class then.
Okay. Is it gonna be done? Since you want the whole thing in 2 parts. Getting dates, getting what they can. Not in a week. Thank you.
Okay, now let's start our tutorial class. Before we start, may I ask, have you started working on your first tutorial assignment? Not yet. Okay, still this Sunday. And you have to complete the questions. I think there are 3 questions. So you have to solve those 3 questions by using the theoretical method, the hand calculation method, and also the software. You need to use software to solve it. Okay, last week we practiced how to solve truss problem. And also we know 1D element include truss element and also beam frame element. So this week, let's have a look another problem. Okay, look, here's the question. Have a look. Oh, sorry. Okay, here's the question. And have a look. And then can you tell me, to solve this problem, how many nodes do we need? How many elements do we need? And how many degrees of freedoms does the node have? Okay. So my questions, how many nodes? Oh. Sorry. Okay, are you able to tell me the answer? How many nodes do we need for this problem? 3, right? Yeah. 2 elements, right? Okay, now can you tell me the coordinates of those 3 nodes? Okay, node 1.
0, 0.
0, 0. Actually here, we don't have any coordinate system here, right? So it's fully up to you which where the coordinate system you want to place. Okay, so yes, we can use 0, 0 for the first coordinate. What's the coordinate of second node?
Oh, I know.
Sorry. What's the coordinates of the second node?
30, 30.
30, 30, right? Okay, what's the coordinate of third node? 0, 30, great. Okay, cool. To solve this problem, we need to have 3 nodes and 2 elements, okay? Then may I ask, how many degrees of freedoms does 1 node have?
3.
Which 3? X and Y and the rotation, right? Great. This is because we are using globe coordinate system, right? So it's not local coordinate system. So 3 degrees of freedom. Okay, so the displacement we always say u, v, and the rotation angle theta. Okay, great. Now, I want to start this problem now together. Okay, so we all agree that to solve this problem, we need to have 3 nodes and 2 elements, right? And also we all agree that each node has 3 degrees of freedoms, right? X and U, V, and theta. Okay, great. Now, we need to create the table. Copy. Okay, now coordinates X and Y, we already done that. And now I want you write down the rest. Okay, I give you 5 minutes. Can you please complete the table as much as you can? For the unknown value, you can just leave a question mark there.
This all that means it's 0 for all displacements, including the rotation.
No. The first one is just the first, you mean 0, 0?
No, for the displacements for node 1 and 3.
Yeah.
Because they're well, I'm guessing there's no rotation either.
Okay, let's fix the support. So no displacement and no rotation. Okay, so for node 1, fully fixed. Node 2, fully fixed. Sorry, node 3, fully fixed. How about the others? And also, how about the forces? Okay, so can you tell me the displacement of node unknown? They are all unknown, right? Okay. Okay, now let's have a look. Those forces. Do we know the force and moment applied at node 1? They are reactions, right? Okay. All of them? No, I mean, for node 1, we didn't know.
Oh, yeah.
We didn't know none of those, right?
Yeah.
Okay, so 3 question marks. How about node 2? Fy
Yeah, sorry, yeah.
fx0, yeah. Yes, because we can't find any x component. How about fy? Yeah. So minus 100, 1200. Yeah.
As well as the distribution.
Give me a equation or certain number about this distribute.
Because the distribution line equals that if you give it.
That's the whole.
Half it, right? Okay, so the total distribute load is 20 pounds per inch multiply 30 inch, then divide by 2, right? So divide by 2, say, 20 times 30,
Yeah.
right? Right? But this 600-pound force will be shared by node 2 and node 3, right? So you cannot apply all the 600-pound force to node 2. We have another one here, right? Okay. So half of this load. Yeah, so another minus 300 load. Is that all? Okay. How about the moment?
It's usually doesn't. It's like negative.
Okay, we have a 1500 inch-pounds moment. You think it's negative? I'm sorry, did you say negative or positive?
Yeah, negative. I think localization.
Yes, clockwise is actually a negative direction.
Depends what you say origin.
Yeah.
There is no origin.
But actually, it depends how we create the coordinate system.
Yeah.
Remember how we create a system? According to the coordinates, we create the coordinates this way, right? So this is x direction, and this is y direction. This direction is positive x, and upward is positive y, right? So we can use our right-hand rule to check the direction. So from positive x, rotate to positive z, positive y. This is the positive z direction, outwards the screen, right? Now let's have a look at this. This one is actually inwards the screen, so it's negative. Okay. So the moment is negative 1500. Is that all?
Oh no, because the node 3 also has.
No, we are talking about node 2 only.
Yeah, no, doesn't that because node 3 is gonna have vertical reactions. Would that affect that create some problem?
I think you get the point, but we need to find out the effects on node 2. Yeah, so nothing about node 3. We focus on node 2 now. Okay, now let's have a look. All the 3 loads we mentioned here. This negative 1200 force is the force this 1200 force is this one, right? The force directly applied to node 2. And this negative 300 is the distributed force. And this negative 1500 moment is directly applied moment, right? But are they all the forces?
Oh, so
Do we have anything else?
I guess you can take that distributed load at the center and take it as a number.
You can't. You can't. There's no point at center. Okay, now. Remember last week we discussed about this tree. We discussed about the equivalent node force. Assume, right? You have a beam, and this beam is subject to those 2 loads. Can you tell me how this beam deforms?
Depends where it's fixed.
Okay, this is not equilibrium problem. Okay, I changed my question. Will this beam bend? No, right? No force can bend the beam. Okay, now I have another beam. Will this beam bend? Yes, right? So, like what we did, we assume those 2 points share this force equally, right? So this force is say 20 pounds inch force, and the total length 30 inch. Okay, so we have 300 pound force here and another 300 force. But if we look at those 2 beams, they have different deformation mode, right? This one remains a straight beam. This one bend. So we have to make adjustments. We have to make sure those 2 beams have the same deformation. What we need to do? They must have the same force and the same deformation.
You apply moments both ends.
That's right. We have to apply moment, right? So we have to apply a moment. And those 2 moments will bend the beam, but won't generate any extra forces, right? Okay, so it is very important. When we convert this distributed load to its equivalent load, you cannot just look at the force. You have to have a look at the moments as well. Okay. Actually, how to convert the force, distributed force to equivalent node force, we discussed it last week. Oh, no, sorry, not this one. Here are the tables can help us to convert the different loading cases to the equivalent node force. And here we have to use the last one, right? This beam is subjected to a distributed load, and there are two equivalent node forces at each node, one per node. And at the same time, there are two moments, right? The left side, the moment is minus W, which is the instant of the distributed load, L squared over 12. And at the right side, a positive value. Okay, now back to our question. To make the same deformation, so we have to apply a moment at both sides. Right? So for this case, W equal to 20-inch, L equal to 20 pounds inch, and L equal to 30-inch. So 20 times 30 squared. And the right side, we need to apply a positive moment. So now, can you answer the question? At node 2, do we have any other loads? Another moment, right? So the other moment is a positive moment. And the magnitude is 20 times 30 squared over 12. Okay, if I'm not wrong, the sum of those two numbers should be 0. 20 times 30 times 30. Yes, so it's 0. Okay, now node 3. Can you tell me the force or the forces at node 3?
The X will just be
Okay, X direction, just the reaction node, right? So we use question mark to represent reaction force only, okay? How about Y direction? -300 minus 300, right? Because both node 2 and node 3 share the force. Is that all?
points for the
No, I'm asking force only.
Fy.
Fy. We are talking about Fy now.
Yeah.
So is this minus 300 pounds the total force applied at node 3? The reactions, right? Don't forget we have the reactions. So We don't know the reactions, but the reaction is not the only force applied at that point. How about moment then?
Same for
Okay, negative 1500. Is that all? And the reaction, yes, plus the reaction. Okay, great. Now we complete the table for the node details. From this table, we have the displacement details and force details, right? So for the beam or frame problem, how to calculate force is a tricky part. So for example, if you forgot to calculate the equivalent forces applied at node 2 and node 3, definitely your solution is wrong. Okay, now.
sorry, just one more question. Just
Yeah.
that last one. I'm supposed to use that over 12. I'm supposed to use that same formula.
Depends on the force.
For-
Say for this one, for the beam 2 to 3, we use a distributed load. There is a distributed load, right? But if you have another load applied, for example, the load is a triangle load or a triangle load or just a moment or something else, then you have to use different equations to calculate the equivalent. Okay, now we can write down the displacement force, right? So that's, we have the displacement. We use 3 nodes and 2 elements for this problem. And may I ask, what is this size? What is the size for the displacement matrix?
6 by 1. 1 by 6.
Why? Okay, we have 3 nodes, right?
Yep.
Each node we have
1 by 9.
1 by 9, right? We have 3 degree of freedoms, so 9 by 1 is not 9 by 1, 9 rows and only 1 column, right? Okay. What are they? 0, 0, 0, right? So for node 1, no displacement, no rotation. And node 2, U2, V2, and rotation theta 2. They are unknowns and they are the solution we want to find, right? Okay, and node 3, 0, 0, 0. This is the node displacement matrix. And also we have the force matrix. Same size, 9 by 1, right? Okay, so what are they? Okay, unknowns, fx1 unknown, y1 and m1, those 3 are unknown. And then at node 2, we do know, right? 0 minus 1500 and then 0. Okay. How about node 3? They are unknown, right? But they are reactions and some forces. So fx3, but fx3 include only one component. So reaction at node 3. Fy3 include the reactions plus negative 300. And the moment include the reaction moment plus negative 1500. Okay, now we have complete the most important part of this problem. And then we have to figure out the elements. So we need to create another table for the element. And for this case, we have 2 elements only. For frame element, we need to have more details. For beam, for bar or for link, we just need to find out the angle, the length, and the Young's modulus, the area. But for frame, we also need to calculate the moment of inertia of this beam. Okay, now let's have a look. For these 2 elements, what's the direction we want to use? For the first element, I already labeled the first element and the second element. Now, can you let me know the direction of those elements? Say, for example, element 1. You want to use the direction 1 to 2 or 2 to 1? Maybe 1 to 2, right? Okay. 1 to 2. Then what is the angle for this element? This is the direction. -45°, right? But I want to know positive 45 or negative 45. Positive, right? Because the direction is counterclockwise direction. Okay, so it's positive 45. Okay, how about the second element? Do you want to use 2 to 3 or 3 to 2? I heard 2 different ways. Okay, let's use 2 to 3. Okay. So if we use 2 to 3, then what's the angle? 0 or 180. That's right. You have to be very careful. If we use the direction 2 to 3, the direction is actually towards negative x direction. So the angle is 180°. Okay, and the Young's modulus, length, moment of inertia, area, we can calculate based on that. Okay, then after we finish those 2 parts, okay, most important part is done. And then we need to calculate. So this is step 1. And then step 2. Step 3 now. We need to calculate the stiffness matrix K. Okay. How we calculate stiffness matrix? Here it is. This is the equation.
So this subject isn't given to us, like you know. It's matrix solution.
Okay, so for this subject, we only have 3 tutorial assignments, right? If you have read the questions, you know you have to calculate yourself. Okay. Oh, sorry. My bad.
Oh,
Okay, now to calculate the stiffness matrix for each of the elements, and this is the equation. But this is actually the one for its local coordinate system. And you need to, because you have 2 elements, and those 2 elements are using different local coordinate system, right? So you have to calculate you have to solve the problem in the local coordinate system. How? Here are the equations. You need to use the K matrix in its local coordinate system, multiply the transformation matrix. Yeah. And the result is this one. Okay, actually here's a typo. So those numbers are not 0. This is a symmetric matrix. Okay, so 2 ways to calculate the matrix, the K matrix. Calculate the K matrix in its local coordinate system and then multiply this transformation matrix. And cos theta, sin theta, and the theta is the angle we just discussed. It's the angle between the local coordinate system and the global coordinate system. Or you can directly use this large equation to do the calculation. So I know it takes time. But you can practice use software like Excel or MATLAB or some other software program help you to do the calculation. Okay, but I would say it's worth to practice. Sometimes if you don't have existing program with you, you need to understand the equations or the principles how to solve such problem. Okay, but of course, I know it takes time to do the calculation. So I won't let you practice the matrix calculation in class. So you can use whatever, you can use any software you think is the most convenient for you to solve the problem. And then once we finish the element stiffness matrix K1 and K2, then you need to assemble it. But luckily for this problem, for this frame problem, node 1 and node 3 are fixed, right? So even though this globe stiffness matrix is so big, but we can remove many columns and rows. So only a 3 by 3 matrix left. Okay, and then accordingly, we can solve for the 3 unknown and then substitute those numbers to the big matrix. We can calculate the unknown for this. Okay, and then we can solve this problem. It takes time to practice. And our first tutorial assignment includes 3 questions. The first 2 questions are about bar and the truss element, and we already practiced that last week, right? And the third question is about the frame problem or the beam problem, which is quite similar to what we have practiced today. When you solve your tutorial questions, I hope you can use the same format like we practiced today. You create a table for nodes and then create a table for elements, and then you can calculate the stiffness matrix for each of the elements and show me how you assemble it, and then what's the final solution. Okay, you can check how long it takes. I would say to solve those 3 questions by hand, at least it takes 4 or 5 hours. But don't forget, you are required to solve this problem by using software as well. Okay, from this week, we will start practicing use software to solve those problems. And let's have a look how long it takes. Okay, that's all for the tutorial class today. And let's have 10 minutes break. We will start our practice lab class in the computer lab at level 4. Okay, and also from next week, we will move our tutorial classroom to computer lab as well. Okay, but we still have our lecture here, but tutorial class in the computer lab. Okay, see you guys in the computer lab.
Are you important to have the lecture in the computer room as well?
I don't think they will allow us to do that.